Alright, so today's problem is word search. This is a pretty common problem. It's kind of a lot of people's and my first introduction into graphs using recursive backtracking. Uh, the problem the problem is a medium, and it states given an m by n grid of characters board and a string word, return true if word exists inside of the grid. The word can be constructed from letters of sequentially adjacent cells where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. So what does this mean, right? So if we look down at this example down here, we see that the word is A, B, C, C, E, D, and we can find this word in there, right? So we don't use diagonals, we don't repeat letters, we're just checking to see if this word exists, if any possible way where we're just moving horizontally or vertically. Again, down here, the word is C, it exists. The word is ABCB, it doesn't exist. Alright, so on theme, let's say that our example is DFS, right? Our example is the word DFS. So how do we go about this, right? So we know that we have to look horizontally and vertically. And we know that we have to check every starting point as a value. So we need to check all of the different values, all of the different possible combinations, starting at this letter A. So we go all the way around here, we go check every single value. We know we need to do that for every single value within. That's where recursive backtracking comes into play. So we need to check every value given this as a starting value, and then check every value given this as a starting value. So the way we do this is by basically making a loop and executing a depth first search for every given value and every given direction. So what do I mean by that? So let's say we start on A, and let's move down here, and then we're at the end here, so we move down here, we're at the end, we move down here, we move down here, we move down here, and then we checked through all of these and we didn't find a solution. But the cool thing is the length of our DFS here, or our string here, is 3. So the moment A reaches, let's say next it checks is B, and then it checks C, well, our string now is ABC, and ABC does not equal DFS. So there's no reason to continue. And actually, even simpler than that is if we check this first value here, and we compare it to the first value in our string here, D, A doesn't equal D, so there's no reason to even continue this search. So then we move on to our next value. B does not equal D, so we move on to our next value. And we do this until we go all the way down and we reach D. D does start. And let's say we check every single direction, every single whatever, every single possible combination until we reach this. This is a solution, so we return true. So how do we actually go about this implementation? So we need to write a few things. So we know we're working recursively, and we know we're backtracking. When we're writing things recursively, we know we need base cases, and we know we need a recursive call. So let's start with that, right? So we know we need base cases, so let's define base cases. We need to make a recursive call, or multiple. And then we need to know, and then we know we need to, what's it called? Backtrack. We need to backtrack and check these recursive calls for every single value as a starting point. And the fourth thing we need to keep track of is we need to keep track of duplicates. So let's say right here, if we started at A, actually let's go back here, right? If we start at A and then we go to B there's nothing stopping us from going back and checking A again, unless that we've marked that we've already visited A. So we need to keep track of duplicates. And basically, we just need to return insert. Yeah. So let's do that, right? So first step is define our base cases. So, well, actually, first step is to define our DFS. DFS function. So we're going to take an M parameter, an N parameter, so rows parameter, a columns parameter, and an element. So this element is the length of our string that we're currently checking. This is what we're going to compare to the length of the word to figure out if our values match up. So let's define our base cases. So first base case is if we find a correct answer, right? So if lm is equal to length of the word, right? So if we find the length of the word, if the size of our word that we're currently on is the same size as the length of the word that we're looking to find, then we know we found a correct answer. So we can then return true. So the hard part is actually defining when we shouldn't return true. So this is going to be a lot of things actually. So if m is less than 0, or if if n is less than 0, so I wrote 2 if statements. Or if n is less than 0, this means that we're out of bounds and we're checking things that don't exist. We're going to get errors. We're going to get compilation errors. So if m is less than 0, or n is less than 0, or m is greater or equal to length of board, or n is greater than or equal to length of board. Let me delete this. And lastly, if word ln does not equal board m n, right? So we know that if our current value that we're checking in our word doesn't equal the value that we're checking on the board, then we know that obviously the rest isn't going to equal, right? So like if I'm spelling the word DFS and the letter that we're checking is A, and that's our first value, we know that we can't spell DFS if it starts with A. It's impossible. So then we return false. So now we get into the meat of it, right? So next step is to actually write this out of order. Oh wait, that doesn't work. Write that. Actually rewrote this out of order. So now we need to keep track of duplicates, right? So we need to, before we continue our recursive call, did it wrong twice. Before we continue our recursive call, we need to keep track of our duplicates, right? So let's first make a temporary value. I keep writing candidates. Temp equals board m and n. So this temporary value is equal to the value that we're currently on. And then we just change board m n to equal a value that can't be within the list. And we know that this pound sign will work because we know that board and word consist of only lowercase and uppercase English letters. So pound sign won't be in our 2D array no matter what. So now we just we do our meat and potatoes, right? Our recursive call. So this is where we go and we check all of the different possibilities. So result is equal to DFS m minus 1 n and element plus 1. So what I'm doing is I'm now basically checking to the left of our current position. So I'm going to check all of the values moving left. And I don't just want to check all of the values to the left. I want to check, for each value, I want to check all of the different depth first searches, right? So I know that I can just do this. Right, so I need m minus 1. Whoops. M plus 1. I need n minus 1 and n plus 1. So now we've gone through and we've checked all of the different combinations, and we've checked all the different combinations with that current value that we're on the board as our starting value. So now we just go through and we change our value back. We change our board value back. And then we just return our result. And now, last step is we need to backtrack. So we need to backtrack, and we've already checked for all of those, given that this first value is our starting value. So now we need to check it with this, and this, and this, and this, and this, and this. We need to actually run our program, essentially. We need to run our DFS. So we just defined it here, and now we need to actually run it. So we need to set up a couple for loops here. I'm just pre-writing this for no reason. No semicolon. So for m in range length board, so for all of the rows, and now for n in range so now we check here, we check all of the rows, and then we check all of the columns. So then our if statement is going to be if our DFS returns true given our m and n values, starting at 0 with our element. If this DFS returns true at our current position, then we know that that's going to be a solution, and we found a solution and we can return true. Else, if we go through all of the different combinations with all of the different things, we can then just return false. Before we submit it, I actually realized I made 2 errors. One was I forgot to include this board 0, so we need to actually check the columns and not the rows. That would give us a wrong answer. And also, I just stupidly forgot to restore this type value. So now we can submit it. And it runs, and it's pretty efficient. And now for the time complexity. So we know that there can be a few different dominant terms, given that the limiting factor could be the length of the DFS, or it could be the not the length of the DFS, the length of the word. So if the length of our word that we're checking is 1, then it's not really a big deal, right? We don't need to check too many paths. We're just checking we're checking 4 different paths to the length of 1. So there could be a few limiting factors when it comes to asymptotic analysis, because the real issue could be the size of the board, right? So m by n. But typically the thing that you're really scared of is the idea that the dominant term most likely is going to be this constant 4 to the power of L being the length of our word that we're checking. So our time complexity is going to be exponential, and our space complexity is going to be linear.